Hi. So in this project, we're going to build a model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam turbines, and heat recovery steam generators to generate power. We have a set of 9,568 hourly average ambient environmental readings from sensors at the power plant, which we will use in our model. The columns in the data consist of hourly average ambient variables, and these are temperature, ambient pressure, relative humidity, exhaust vacuum, and net hourly electrical energy output. In single-cycle gas turbine power plants, natural gas and compressed air are used to generate electricity. Air is drawn from the atmosphere, compressed, and fed into the combustion chamber. By injecting natural gas with compressed air and igniting it, the combustion produces high-pressure hot gas steam that spins a turbine. This spins a generator that is connected to the turbine to produce electricity. In single-cycle gas turbines, much of the energy is wasted as hot exhaust, with an energy conversion efficiency of 35% or less. In a combined cycle power plant, waste heat is captured using a heat recovery steam generator, providing an even greater energy conversion efficiency to produce more power. A combined cycle power plant generates electricity by using both steam and gas turbines. The waste heat produced by the gas turbine is used to generate steam, and that steam is fed to a steam turbine to generate more power. This increases the amount of energy produced by up to 50% for the same amount of fuel, as well as increasing the efficiency of the plant. Combined cycle power plants, or CCPP output, depends on atmospheric pressure, exhaust steam pressure, ambient temperature, and relative humidity. Predicting the full load electrical output of a CCPP is important for the efficient and economic operation of the power plant. So we will develop a machine learning based model to develop a predictive model for a CCPP. So the problem described in the project topic section will determine what type of machine learning approach is needed and select an appropriate output metric to evaluate the performance in accomplishing the task. We will then determine which possible features we may want to use in the model and identify the different algorithms that we might consider. We will split the data to create a test set to evaluate the performance of the final model, and then, using our training set, we will validate our model. We will use our validation approach to compare two different model algorithms to select the model with the best performance on our validation set as our final model. Finally, we will evaluate the performance of our final model using the output metric that we defined earlier. So in this problem, we're facing the need to predict the output power by using some parameters. So we are facing a regression problem. The machine learning approach that best suits our case is supervised learning, the process of learning to map an input to an output using examples of input-output pairs. In regression problems, the end goal is to calculate a value by capitalizing on the relationship between the target variable and other variables. So as our models, we'll use linear regression and random forest regression, and our metrics will be the mean squared error, root mean squared error, and mean absolute error. Okay, so what we're going to do is develop two regression models using linear regression and random forest regression algorithms on this dataset using a combination of all features, temperature, ambient pressure, relative humidity, exhaust vacuum as predictors, and net hourly electrical energy output as our target variable. After loading the data and importing the Python libraries needed, we will first split our data into a training and a test set. The training set would be habituated to engender the mathematical model of the relationship between the features and the target variable. So to do this, we will split the dataset into an 80% training set and a 20% test. Now, we will use linear regression and random forest regression to develop our model. And we will evaluate the performance of our model using three performance metrics: root mean squared error, and mean absolute error. Now that we have evaluated all our models, we can see that random forest regression algorithm has the lowest root mean squared error and a mean squared error of 0.9644, which means that 96.44% of the variation in the target variable of net hourly electrical energy output can be explicated by the model. Random forest regression algorithm thus gave us the best performance. Thank you.